Hi and welcome back again. We're going to continue on with our idea of HL bonding, and we're going to start looking at formal charge. I know some of you are slightly familiar with this, but we're going to put some rules around it and talk about where we will see this applied to questions and what we need to know. So let's get started. Essentially, what we're going to be talking about is how formal charge can be used to assess the stability of delocalization and resonance structures in molecules. We've recently revisited the idea of delocalization and how resonance structures come about. So let's have a look. So resonance or delocalization of electrons, so anytime we have delocalization of electrons across atoms in a molecule, we will get what we call resonance. This is where we have two or more equivalent resonance structures, i.e. we can draw out Lewis dot diagrams or resonance structures where the bonds are in different positions, but they all fit the bonding rules. So we don't know which atom has the extra electrons or where that negative charge is or where the double bond goes. Okay, so what we're talking about is this electrons moving across our structures. And we've seen this already anytime we have something like an anion of a carboxyl. We said that the resonance hybrid for this is actually that half, not quite a double, not quite a single sort of bond order 1.5, where we have resonance where it can either be the C double bond O minus this way, or we could actually have O minus C double bond O this way, and that it will flip between these two structures continuously on the atomic time scale. So each resonance structure shows a different way in which the lone pair and bonding pairs are arranged. The bonding pairs and lone pairs can be interchanged between the two or more resonance structures that can be drawn. So the resonance structures do not truly exist. We know that the average structure, the resonance hybrid, is the true representation of the molecule. So the average of each resonance structure we call the resonance hybrid. When we come to expanding the octet in the new molecular geometries that we've talked about with molecules such as sulfur and phosphorus, things get a little bit more complicated. In atoms that can expand their octet, we are often faced with additional possibilities when drawing the resonance structures. So in this case, we can have the SO2 with the double bond and single bond with 6 electrons around the oxygen, and then the one bonding pair giving it 8. This now has 2, 4, 6, 8 here. But because it can expand its octet, we also have this resonance structure here, where the sulfur has 2, 4, 6, 8, 10 electrons on the central sulfur atom. This, for most molecules, would not be possible. It breaks the 8 electron rule. However, we know that sulfur can expand its octet, so this now becomes a viable resonance structure. We need to consider the possibility of this one. When we look at this, formal charge is the way that we can determine which will be the most stable structure, and therefore the one we're most likely to see, remembering that with molecules they will generally tend towards the most stable arrangement. So formal charge is given by this formula here. So formal charge is equal to the valence electrons minus half the bonding electrons plus the lone pairs. Make sure you write this one down. This is a formula that is not given in your data booklet. You do need to memorize it. So when we calculate the formal charge for each of these molecules containing sulfur, the structure with all formal charges equaling 0 on each atom is going to be the most stable. So we need to look at first our first resonance structure here. We have sulfur, and it has 3 bonding pairs, 1, 2, 3 bonding pairs, and 1 lone pair. So substituting into our formula, which was formal charge is equal to the valence electrons minus half the bonding electrons plus the lone pairs, we end up with 6 valence electrons, okay, minus we have 6 bonding electrons. Essentially, this can be bonding pairs. Okay, if you count the bonding pairs, what you're doing is counting half the bonding electrons. Okay, so 1, 2, 3 plus 2 lone pair electrons, so 1 lone pair, so 2 electrons. So we get 6 minus 5 is equal to plus 1. You've got to remember bid mass in this and do the stuff in the brackets before you subtract from the number of valence electrons. So on this one, we have a plus 1 charge on the sulfur. We then can calculate that for each of the oxygens. The left oxygen has 2 bonding pairs and 2 lone pairs. So this is going to be 4 electrons that are bound up in lone pairs, and then we have 2 bonding pairs, so 4 divided by 2 is 2. So we're going to have 6 minus 6 is going to be 0. And then on the other oxygen, we only have 1 bonding pair now. So this is going to change to 1 plus 6. So we're going to have 6 minus 7 is going to be minus 1. So we have 0 plus 1 and minus 1. If we continue to calculate these using exactly the same formula for each structure, this one here will be plus 1, same as it was before because it still has the same type of bonding arrangement. This oxygen now is minus 1 and this one is 0. If we look at this one, things change a little bit. Sulfur now has 6 bonding valence electrons still, but it has 4 bonding pairs. 1 lone pair, so 2 lone pair electrons. When we calculate out, that will be 0. For the oxygens, 2 bonding pairs and 2 lone pairs. So we get 6. 6 minus 6 is equal to 0. And then for the last one, it's exactly the same, so it will also be 0. So what we see here is that this will be the most stable structure. It has zeros, no formal charge on any atom. So these structures still exist all at the same time. What formal charge tells us is the one that we are likely to see most of the time. We call this the main contributor to the resonance structure or the resonance hybrid. Because the hybrid exists somewhere between each of these, there's one that's more stable than the other, so it will tend to spend more time in that form. So the sum of the formal charges of a molecule must be equal to the overall charge. So if our molecule, such as SO2, is neutral, then the formal charge must be 0 overall. So if we go back here, this plus 1 minus 1 situation is going to be 0 and 0. So these are all legitimate formal charges for this molecule. Okay, so they all are valid. There are limitations to formal charge. It's useful in determining the stability of a resonance structure, but it does have limitations. Using the rule does not account for electronegativity influences on the atoms, remembering that more electronegative elements are able to stabilize a negative charge a lot easier, or charge changes more easily. So if we want to predict the most stable structure, we need to consider first the lowest formal charge on all atoms, so we're going to try and make it 0. Any negative charges are placed on the most electronegative atoms. What I want you to do now is pause the video, have a look at the 2 resonance structures given below for N2O, calculate the formal charge for each atom, and then using these considerations, lowest formal charges on the atom, so we want as many at 0 as possible, and the negative charge placed on the most electronegative atoms, remembering you can refer to your electronegativity table, I want you to work out which one of these would be the most significant contributor to the resonance hybrid. Once you've done that, come back and check your answer. Okay, I stitched you up a little bit there. There's actually an error in this structure here. You needed to have a triple bond there. Sorry about that. But if we have a look at this and we now calculate them, you can see that we have -1 on this nitrogen, +1 on this nitrogen, and 0. So this is -1, +1, and 0. Then we would have 0, +1, and -1. So if we have a look at these are valid structures. If you didn't realize what was going on here, you ended up with an invalid structure here in that you wouldn't have the sum of all the formal charges adding to 0 if we didn't have that bond there. This one would actually be +2, and we can't have that. So something was wrong with the structure. So that double bonded nitrogen was not actually a valid structure, which is what tips us off there. Okay, so +1, -1, +1, and 0. Okay, 0, +1, and -1. So if we have a look at these, taking into consideration the lowest formal charge on atoms, we have that. And then all negative charges are placed on the most electronegative atoms. In this case, we have on our nitrogen here, so 1 would be the preferred structure. So if we have a look at this, when we're talking about main contributors, this is what we're talking about. If we have something like this anodic oxygen here, okay, anionic oxygen here, there's no resonance. There's no way for a double bond to occur with just the hydrogens here. However, if we look at the structure where we change this to a C double bond O minus, the negative ion of our carboxyl, we'll actually see that the electronegativity is evenly distributed across these two, which indicates that the hybrid is actually what's happening. We don't have one part of this group being more negative than the other. Again, if we see this situation here with the carbonate anion, okay, this is your carbonate CO3 2- anion, which is one that we should be familiar with for resonance. The electron density is distributed evenly around this shape. So the resonance hybrid is showing that the electron density isn't staying in one particular place. Same here where we have the NO2 ions, where our plus and our minus here. Okay, we have even distribution. When we look at this structure here, okay, where we have a ketone and a negative charge, we're able to move the electrons this way or move the electrons that way. However, we are seeing the significant region around here with the more negative in the center. This, if we work out formal charges, would be the major contributor to the resonance hybrid. So it's actually a little bit more negative up in this region than here. We can see that it's still bouncing between the two. We have negative density between those two, but that one is stronger because it is the major contributor, and that will be because the negative charge is on the more electronegative atom, being the oxygen, making it the more stable resonance structure. So when we figure out resonance structures, essentially we need to have the correct solidal structure forming bonds by pairing electrons using our Lewis dot rules. We form additional bonds by pairing electrons to attempt to satisfy the octet, remembering that some structures will be able to expand their octet if they have sulfur and phosphorus in particular. Then we have a look at the structures to see if they're valid. In this case, the terminal N is octet deficient. There is not enough. There's only 6 electrons around this one. This one has too many electrons. It has 2, 4, 6, 8, 10 electrons. Nitrogen can't expand its octet, so this is not a valid structure. Okay, we move the electrons usually in pairs to generate valid structures, and this is that one that we were looking at before. So we can have this two double bond situation, or we can have a triple and a single. Okay, where the lone pairs are not on this central atom. So moving this lone pair makes this nitrogen now valid. Okay, so these are the different contributors we could have to these resonance structures. So you always need to check if it's valid, look at the formal charges, then put the negative charge on the more electronegative atom, and that will determine your major contributor. That's it for formal charge and resonance, and I'll see you for a look at ozone in our next video.